Welcome everyone. So good to see you here today. I hope you can hear me. It's so nice to just connect with you in the chat as well. So please continue to connect with us and connect with each other there. Welcome to the PyDP launch event. My name is Helena Barmer. I am hosting this event today and I'm also the lead of the OpenMined online events team. So if you're new to the community, please give us a thumbs up in the Zoom chat so we can welcome you properly. Just write the letter B in this fashion, you can see it, and then we will know and we can just say a huge welcome to this community. So before we go ahead, just a few quick Zoom guidelines. You will all be muted by default, so you know this. It's only us panelists who will be able to speak. If you have a question for one of the speakers, you can ask this in the Q&A box. You can see this if you're on in the Zoom app at the bottom, just Q&A, push that or click that and just ask your question to one of the speakers today. If you have a general question or if you want to know how to join our Slack community or anything like that, just write this in the Zoom chat. I will be there to help you. And any other questions, just let me know. I will be there. So our speakers today are Trask, Szymkow, Chinmay, Shah, Lukasz, Kozuchowski, and Kritika, Prakash. Very happy to introduce them now, but first out is Ben. How are you, Ben? Are you here with us?
Hello. How's it
Hi.
going? Fantastic. Thank you everybody so much for joining this event. It's the launch of OpenMind's PyDP library, which is a Python library for differential privacy. Very excited to be able to share with you today some demonstrations and a whole lot of other really interesting content. I guess this library has been 6 months in the making, and there's a great story, and we'll get to. And you're gonna hear the story of how it came to be and all the functionality that it provides shortly. So I wanted to just, before we kick off, is just talk a little bit about each of the folk that will be speaking and the amazing efforts they've put in. So our founder of OpenMined, Trask, he'll be speaking first, and he's gonna, I guess, position differential privacy, remind us all about the OpenMined community, and invite anyone here who's not already involved to please get involved. But he'll kind of, I guess, position differential privacy in the context of OpenMined. We then have Chinmay. So Chinmay is quite a remarkable individual. He leads the engineering team for PyDP, and he's spent a long time trying to get through a lot of really tough issues. And one of the fantastic things he's been able to do is work very closely with Google's own team. So this library, as you'll hear, it was originally based on providing a Python version of Google's differential privacy library, which was built in C++. Google's differential privacy library is, it's battle tested, it's deployed already throughout, it's got a history of working and doing the job. So he'll be talking a little bit about his team and what they've done and the features. And we also have Kritika. So Kritika Prakash is our lead researcher in the differential privacy area of OpenMined. She's been working on many different use cases for differential privacy, and she's going to give us a primer on differential privacy, what it means, what it's positioning, and she's going to give us a little bit of maths. So don't be scared. There is some maths involved, but it's not terribly hard. But really, it's just running through what it actually is and how it works. And then we've got a mystery demo from Lukasz. So Lukasz leads our exotic libraries team, and he works on a lot of the Java machine, the Java virtual machine languages side of things. And I guess we decided that we weren't going to stop with Python. I won't spoil what he's going to show, but it's something pretty special, especially for the machine learning and functional programming community. I won't keep you any longer, but we'd like to pass along now to Trask, and thank you so much.
Hi everyone, thanks Ben. And yeah, welcome everyone. Thank you so much for coming. Thanks for being here. Huge congratulations to everyone who's contributed to the development of these DP libraries. And this represents a really amazing milestone for our community. So as Ben mentioned, differential privacy in particular is a cornerstone and a key technology that we need in our societies to be able to achieve, a privacy preserving future. In particular, when we think about its application to scientific endeavors, if we can get to a world with mature differential privacy infrastructure that makes its way into everything from the phones that we're using to the websites and desktop apps that we create, it really opens up the potential for us to learn high-level insights, such as causes for cancer, or causes for whether products are good and bad, and whether basically to learn patterns across humanity while being able to keep individual records secret, right? And that as a social impact is truly unprecedented, and is what makes differential privacy as a technology such an exciting component. If we zoom out a little bit and sort of consider the broad goals of what we're trying to do, if you'll find on our website and on GitHub, we talk a lot about lowering the barrier to entry to privacy preserving technologies as a strategy to make the world more privacy preserving, right? So if we sort of consider this broader mission of there's lots of people that care about privacy, that want privacy to be able to happen, but adoption is really expensive and challenging, and the libraries can be really complex. Often they're written in languages that are perhaps really difficult to deploy, such as C++, which is sort of less accessible, particularly to the machine learning community. And then the other big sort of challenge of lowering the barrier to entry to privacy preserving technologies is that often they're sort of untested. It's difficult to write cryptography code. It's difficult to prove that cryptography code is sort of valid and trustworthy, and that we can really trust it to protect our information. And that's what I think in this particular case is so special about this project, right? It's taking a C++ library that is just absolutely battle hardened, but perhaps not sort of natively mission ready for a lot of different environments, like data science or mobile phones and these kinds of things, and really building the bridge between battle hardened code that's been deployed to millions of devices already, that we can sort of trust to be kind of the correct implementation, and it's really robust in protecting information, and then building a bridge to all the different types of languages and deployment environments, such as Python, that we want to be able to use it in. I can't understate enough how important this is to our mission at OpenMined and to society's sort of broader goal of achieving a privacy-preserving world. Because in order for us to achieve a privacy-preserving world, we need good, strong, trustworthy, general-purpose, easy-to-use infrastructure. And that's what I think makes this project so special. So yeah, thank you everyone for coming today. Super excited about this project, super excited to release, and a huge shout out to everyone who contributed to the code, from the leaders of the project, several of whom you're going to hear from today, but also to people who, committed just individual commits or some of your first pull requests along the way. So yeah, and with that, I'll hand it back.
So I think we have Kritika up next to position differential privacy and talk a little bit about the theory behind it and how it's going to be used. So Kritika, are you there?
Hello. Yeah.
Fantastic. I will leave it in your very capable hands.
Okay. I hope my screen is visible to everyone.
Yep.
All right. So, hello everyone. I'm Kritika. I lead the differential privacy research team here at OpenMined. And I'm just going to talk a little bit about the basics of differential privacy. So, basically, the problem that we're kind of trying to solve is, if you imagine an adversary or some sort of an attack, which is attempting to infer whether a specific target user is a part of a data set or it's not a part of that data set. And just by knowing whether that person is a part of the data set, it can infer a lot about the person. So something like that would be considered a membership inference attack. And so normally when you are trying to work with any function that you want to compute that helps you achieve some goal, you have some input data, you operate on it using some sort of query function f, you get a result which would be f of the data set. And now if you consider a data set very similar to the original data set D, except it only differs from the original data set within one record or one user. And in that case, the final output result that you're going to get through the pipeline is going to be different. And this difference in the final result is what can be used to exploit the data and to get information about the actual input data. So differential privacy, it's adding the right amount of noise in a very smart manner to mask individual contributions, whereas you're still not changing the bigger picture of the, you're just not changing the bigger picture. So, and the reason the need to add noise arises is because the user data is quite sensitive. It could be about people's health, it could be about their political views, it could be anything. And if you are able to guarantee privacy to the users, you make it more accessible for better users and probably better applications. And so, and the ease of computation of differential privacy is significantly better compared to probably other privacy preserving techniques such as strong cryptographic algorithms. And the aim is that we don't lose out much on the utility, but at the same time, we preserve the privacy of the users. So more mathematically speaking, if we have two neighboring databases, D and D prime, which differ in exactly one data entry or one user, then any algorithm M is said to be differentially private if the probability that after applying the algorithm M on the databases D and D prime, the probability that you get the same result is bounded by a factor of e power epsilon. And in this case, epsilon is a very small value. So e power epsilon is also going to be a very small probability ratio. And this mathematical framework helps us understand what it means for someone's data to be private. So in the DP, in a differentially private pipeline, what you will be doing is that at some stage of your original pipeline, you will add noise to the data. And finally, the result that you get, the function, the query that you're working with, when you apply it to D and D prime neighboring databases and you add certain noise to them, the result that you get will basically be the same. Like it will be the same in many cases, and sometimes it could differ mildly. So probabilistically speaking, it will be the same. And one example of that I can give you is consider the number of visitors that visit a restaurant at different hours of the day. So maybe here this graph says that there are 10 visitors visiting the restaurant at 3 p.m. and so on. So this is the exact data. This should be private. So what we're going to do is we're going to use a Gaussian distribution to add some noise to it, which will be based on some handpicked parameters that we want, such as epsilon and delta, and that will define the shape of the Gaussian distribution. And we add noise from this to the original database so that it looks something like this. So if you look at the orange distribution, that's the final distribution. And even though it is different from the original distribution, it varies very slightly so that you still get the bigger picture. You still get an idea of what's happening. And at OpenMined, we work on various projects around differential privacy, both from a research aspect and from a development aspect. So one class of projects would be building libraries that support local differential privacy, local in the sense that data is applied as close to the data as, noise is applied as close to the data as possible. Another big project that we're working on in different applications is making deep learning differentially private. And some other important things would be making SQL queries private and validating differential privacy automatically. Another more educational project that we are focusing on is writing tutorials, basic tutorials, which can really help people implement and understand DP, especially in the context of PySwift. Some more applied projects that we have been looking at is how to make contact tracing for COVID more private and how to make hospitals collaborate with each other to make better AI tools for medical data, how to make such pipelines private. So I hope I didn't go too much over time, but that is everything that I had to convey to you. Thank you.
Thank you so much, Kritika. That was absolutely fantastic. So we're going to hand over now to our engineering lead for Python, the PyDP library. So Chinmay, have we got you here?
Yep. Hey guys.
Fantastic. All right. There you go.
Yep. Good evening, everyone. Hope all of you are having a great day. Thank you for tuning into the PyDP celebrations. I'm Chinmay Shah from Mumbai, and I lead the PyDP team here at OpenMined. Little about me, I'm a class of 2020 graduate, and I love building impactful technologies. So let me just start sharing my slides. So PyDP is under the OpenMined umbrella, which is led by Andrew Trask. Trask is a PhD student at Oxford, as well as a senior research scientist at DeepMind. He believes strongly in privacy-preserving machine learning, which led him to start OpenMined. OpenMined already has 8,000 plus members on Slack, so if you want to join in, please join in. Next, we have Ben, who leads our development teams over here at OpenMined, and he has been guiding us throughout the project. Thank you, Ben, for all your help. Kritika here leads the DP research team. She's currently finishing a master's thesis, and her greatest gift with us is like she can convert any complex research problem into a simple intuitive form. The PyDP team is very grateful to have all these folks guide us throughout the process. PyDP has contributors from across globe. We have people from all the continents except Antarctica, of course. So we have folks from US, Canada, Brazil, to like bunch of countries in Europe. Now, like many of our contributors are from the Indian subcontinent, same place from where I am. And on the eastern side, we have people from Philippines as well as Australia. So together, we guys make up more than 10 plus time zones, which kind of makes holding meeting difficult. I want to give a shout out to almost each. Hold on. Yeah. I want to give a shout out to each member who has contributed to PyDP, whether they have created a commit or raised an issue, because each of these contributions are really valuable to us. A special shout out to Alessandro, Benjamin, and Saksham, who are very active developers these days. Special shout out to also Frank. He's our release manager, and he makes sure that all our release notes are in highest quality. Also, I want to thank Shah as well as Aljit, who made sure that our documentations are in very good standards and are up to date. And these days, we are coming up with our own demos. So I want to thank Daniel, Shasta, and Frank for putting together all these demos. And while at PyDP, we do have some engineering expertise, we sometimes lack. So we had Ayub as well as Banaldi, who came to rescue PyDP when we had trouble fixing our CI pipeline. So I want to thank all of these folks, and also a lot of folks came in and out and helped us throughout the process. So sorry if I missed your names. In the past few months, as we developed PyDP, we in the past few months, we have achieved a lot. Our package is on PyPI, which supports OS X and Linux. And starting Tuesday, when we release the stable version, we'll also be supporting Windows 2. If you're a Docker fan, you can find us at OpenMined/PyDP, and you can find the Docker image. Some statistics, we have 30 plus contributors, 450 plus commits, and 200 plus PRs. And on PyPI, we have more than 10,000 downloads. Yeah. So with this launch, when we release the stable release, we'll be supporting the full Google's differential privacy library. At PyDP, we get to work with folks at Google, as Ben mentioned. We have worked with the original authors who have written the code. Also, we have actually contributed to the Google's library. So Benjamin from our team has pushed code on the Google's repo, so that now even these guys are going to support Windows 2. For reading the documentation, you can go to pydp.readthedocs.org. So as I mentioned, at OpenMined, differential privacy is going to be an integral part of privacy preserving machine learning. And when Google open sourced its library back in, September, we got into action and trying to integrate it. The reason being that it was written in C++, and for many data scientists and machine learning experts, they use Python. So it felt that we need to make this library more accessible. So between September and April, when we released our first version, we had a lot of hiccups, starting with how to wrap this. Should we use PyBurn 11 or Swig? As we progressed, we had to decide between the build system. So we had a CMake as a build system, or which PyBind uses, or like Bazel that Google uses. So thanks to Ben, we actually cracked this problem, and we finally got it working with CMake, with Bazel. And a huge shout out to Vishal, actually, who got the C++ code working with Python, because we have to generate the SO files for the integration. As we progress further, like in January, February, when we started integrating this code, a lot of Google's code was written using C++ templates, which makes it inherently difficult when using PyBand 11. So Alessandro took the inspiration from the TensorFlow, and we got it working over here. And eventually, in the first release in April, we got the Carrots demo, which is the Google's demo itself. So we ported that to Python, and we got that working on Linux with some limited functionality. So since the launch in April, we had our own journey. We were rapidly developing and pushing. We got Docker version working well as now OS X2 in last few months. And speaking today, when we release the stable release, we'll be supporting Windows 2. All of these libraries supports Python 3.5 plus. And as we mark this stable release, we're putting yet another milestone in front of us, that by Feb 2021, we want to do a lot more operations within which we want to support in PyDP. So what do you get at PyDP? We currently support all the Laplacian noise mechanisms. Along with that, so you get functions like bounded seam, bounded variance, bounded standard deviation. Along with that, like statistical operations like mean, max, and median. Also, we support quantitative operations like count and percentile. And right now, we are actively developing to make this system repository support a distributed system. So right now it's still in testing stage, but when it will be production ready, it would be we aim to build scalable and production level distributed systems using PyDP. Few of the things that we are working on along with is that we have taken few major initiatives. We believe that engineering and research needs to go together, like they're two peas in the same pod. So keeping same in mind, we started two major initiatives. One of is PyDP and research. So we are working closely with the research team to build better technologies. One is the DP-SQL project, where so the problem arises when you want to apply differential privacy on SQL queries, because what happens is we need to analyze each and every query and understand that they don't violate DP principle and don't end up violating user privacy. The other issue that we are working on is selecting noise mechanisms. Since in a couple of months, we are going to support tons of noise mechanisms within Laplacian. So we'll put up a framework on how to choose these noise mechanisms and also maybe automate that part. Along with that, we are working closely with the different research projects. So at OpenMined, we have a set of amazing researchers and engineers. So we are also providing engineering support to this research project. So one of the project is the DPF project. We are working with a team at Archon led by Lucille, where we aim to use the federated learning in combination with differential privacy to share hospital data across networks so that we could build better diagnostic capacity and learn from the combined knowledge. We are open to more research projects, so just drop us a line if you want to come up with this thing. So coming up with this new vision, so what we want is we are going to call this PyDP a one-stop for differential privacy. So if you want to do any DP operations, you should be able to do using PyDP. So achieve that, we have identified 4 major key sectors that will be actively contributing or working on. First one is adding different noise mechanisms. So right now we just support Laplacian, but in the coming months, we want to support other noise mechanisms such as geometric, Gaussians, or uniform noise mechanisms. Other than that, we want to integrate PyDP with the database system so companies can start using it within the production systems in itself. So right now what happens is like you have to pass a list to PyDP, or you can manually fetch the data from database and put it into list and push it to PyDP, or maybe simply use pandas, but that's not something that's you can use at production level. So what we are going to do is integrate SQL databases such as Postgres and SQL, MS SQL, as well as non-SQL database, also MongoDB. So we're going to start that integration soon. Also, what we believe is that differential privacy is going to be building block for privacy preserving machine learning. And to achieve that, we need to provide machine learning and deep learning capabilities. So we are also going to focus on that. And the fourth major sector that we identified is at large corporations, data is not always stored in SQL databases. It's stored in large data warehouses. So what we are going to do is we are committed to help these companies build add DP capabilities to their workflows. So in coming months, we are going to add support to Apache Beam. And if organizations feel that we need to add more warehouses, we are happy to explore that. So to achieve this milestone and to this new vision, we have identified 5 key sectors or 5 key verticals where we're going to focus all our energy on, and all of this is going to be in parallel. So the first one is building tools to do PyDP better. So first one is the privacy budgeting tools to manage your privacy budget. We also want to add support to distributed systems. So if you have data across multiple systems or multiple zones in EC2, then in AWS, then you should be able to do it. The third is like PySwift integration. That is something very dear to us at OpenMined. So we want to integrate PySwift with PyDP. So that's our idea. At a database vertical, we want to support SQL databases as well as non-SQL databases. Along with that, we want to support ETL systems as well as Apache Beam, as I talked earlier. Also, we are going to focus on a new vertical called something known as basic research. So we are going to integrate tons of different libraries together. So we are going to integrate our DP, OpenDP by Microsoft and Harvard, as well as IBM DP. So hopefully we'll be working with those organizations as well. Other than that, we are going to integrate machine learning techniques in PyDP. So if you want to do logistical regression, linear regression, or PCA or any machine learning algorithms, you should be able to do it within PyDP. We're also going to focus on delivering on a custom DP functions. So if you want to write let's say your own functions or something like that, you should be able to do that using PyDP. So let's say you want to find the 100 moment or something that's not provided by us. So if you want to do that, we'll be providing that functionality. And the fourth major pillar we are working on is going to be the documentation pillar. So we identified that all these engineering efforts are useless if people are not able to use it. So our very major focus is going to be on proper documentation. So we are going to also create different use cases, both on a data set, like a synthetic data set or Kaggle famous data sets, or also working on the real world problems. So we're going to do all that and create different use cases for everyone to identify whether they could use DP in their pipeline. Other thing that we are working on is creating different benchmarks. So what we identified is like different algorithms can be in you can write different algorithms, and you can also write in algorithms using DP. So we want to compare how each of them perform. We also want to benchmark across different mechanisms such as the IBM DP, PyTorch DP, or let's say we have any other open DP. So we want to compare these different mechanisms as well, and we want to benchmark these. And the fifth major vertical we want to focus on is with closely working with the research team. So as we said, at PyDP, we're going to focus on lowering the barrier to access cutting edge DP operations. To achieve that, we have identified few ideas, such as local differential privacy. So adding noise at the local level before you actually send out data to the network. Also, we are doing something known as auditing the DP operations. So we have Patrick Hunter who leads the DP audit team. So what they do is like they make sure that our code that we have written adheres to the theoretical proof as suggested in the paper. And also, as Kritika mentioned, we are doing DP SQL. So we want to protect, if you want to apply DP to the SQL queries and protect from MIA attacks, we should be able to do that. And of course, private deep learning, which is something essential and that we all do. Laying this bold plan in front of you, I invite you to the journey of building better privacy preserving ML tools and make it more accessible. So tomorrow when we build new technologies, we should have privacy built in. So I would like to say that world of DP is in quite infancy, and it's at the same stage where deep learning was in 2010. So in coming years, it's going to shoot off. So if you want to join us, you can apply at placements.openmind.org. And you can also find a PyDP repository on OpenMined/PyDP, or you can find the documentations at pydp.read.org. If you want to chat with the team, you can find us at libpydp on OpenMined Slack. And if you want to contact me, you can contact me at Chinmay899 on Twitter or at Chinmay on Slack. So, thank you.
That was absolutely fantastic, Chinmay, and an incredible That was an incredible journey through everything that we've had to achieve on PyDP. And I think hopefully everybody that's watching here can really help us celebrate all the efforts of the big team. I think there's 25-ish contributors there. Chinmay, I think you said you might have a demonstration to show us. Is that right?
Yep. Yeah, I'll just start a demonstration also. Cool.
Perfect. Well, yeah. And again, thank you, Chinmay, so much. I think it's very, very clear the incredible hard work that's gone on to make this come a reality. So let's pass it along to you to show it in action.
Okay, perfect. So Kritika in the beginning told us about MIA attacks, or like what differential privacy actually is, but like what if you want to see it in action? So what we have done is we have created a synthetic data set with 5,000 records of personal information such as email ID as well as name. And what we are showing is how you can use PyDP to protect yourself, to protect differential privacy and protect from MIA attacks. So in this data set, we have identified something known as sales amount for each user. And in this notebook, our agenda is going to be, we have two different data sets. So one is the data set that's created using 5,000 records. And the second data set is like, we just removed one record from it. So we're going to identify whether we could identify that one person using a different operation. So let's go. So at the start, we import PyDP. So we have to install Python DP. So it's already on PyPI, as I already told, so you can download it. So let's start. So we have 5 different databases, which are already up on our GitHub. So we're just loading them up using pandas. And we're just combining them. Okay, so now what we are doing over here is we are removing one person from the record. So this is the first record in our data set, and we're removing that person. So so in the second data set that we have, this person does not exist. The first record, if you see over here, Osborne. So to identify that, to see if PyDP works, so what we're going to do is there is a statistical number called sales amount. So if we take the 2 data sets, so if you take the original data set and take the sum, and if you take the new data set and take the sum, the difference should be about 3194. That's a sales amount spent by this guy. So what we're going to do is we are going to apply differential privacy to see if we can actually are able to find out whether we can find out 3194. So let's assume you have another database where you have all the sales number as well as the credit card ID or anything. So you can actually figure out that that was actually Osborne who bought something for 3194. So let's see. So over here, what we do is we just do some basic testing that we took the sum of original and the different and the directed data set and found out that sum is actually equal to 3194. So now let's start using PyDP. So we are going to use something called as bounded sum. So that's our equivalent of sum on the differential privacy side. So what you could do is we are taking epsilon of 1, and in the data set we have generated, we have kept that the minimum amount you have to spend is 5, and upper limit you have to spend is 250. So that's the lower and upper bound we are setting. And since the spending is a floating point number, so we have to specify float. You can also set this as int if you want to save tons of memory. So what we are going is that we are resetting the data and adding all the data to the PyDP algorithm, and over here when we print the results, it's actually 60. You can say it's 367. Hold on. Yep. You can see that this actually works. And if you see the original amount, hold on, cannot put that up. Okay, this is just taking the sum of this original of the start without on the original data set. So in the redacted data set, we again we again apply PyDP on bounded sum. We again add the new data, and you can see that this time the sum is a bit different. So if you actually see the difference in the amount, that's like $126. So that's quite different from 3194, as you can see over here. So so here we are saving Osborne from the MIA attack. So if you have compared 2 different data sets, you're not able to actually identify that who actually spent that amount. So we're able to save Osborne's privacy over here. As you can see, some of value in original data set and some of using DP, that's a bit different. Now in the redacted data set, we again found out there's this sum, and when we found out a different itself, it was 126. So privacy is saved. So at PyDP, we have actually built something very cool. So let's say if you have a stream of data coming in, let's say like if you're getting a stream of data. So for example, you get one database first, and then a couple of hours, you get another data set, but you have to provide continuous reports on them. At the end, your combined data comes together. So what you can do is like, you can actually do that using PyDP. So, so let's again start the same operation. So again, we organized by bounded sub, and over here, what we did was we divided this a data set into two parts of dividing 3,000 and 2,000 records. So let's say first, let's add to 3,000 records of PyDP and start the operation. Yeah. And so we are saying that we are left with budget of 1 because we started with epsilon of 1. So we are left with budget of 1. Now what we are going to do is, let's say if you only like you have a fixed budget, you don't want to waste all your budget on this one operation itself. So what you could do is you know, I want to use privacy budget of 30%, and you can actually find a sum. And we could see that if you find the actual sum, there's a difference of $1,000, 1,000 rupees, and or dollars, whatever currency you want to consider. So that's because of this issue, because we are just using 30% of, you're using just 30% of privacy budget available to us. So that's the reason there's this huge difference. So now we are left with 70% of our privacy budget. And what we do is we add up the remaining 2,000 records that came into our stream now. So we again do the privacy sum, and we find out privacy left, and you can actually see that this time the sum is different. So if you want to compare on how things actually turn out, the actual sum of the whole data of the 5,000 records is 63594. And when we ran with the when we did the sum with privacy budget using the full privacy budget, it was 661, and it was 661. And when we use privacy budget, when you use the differential privacy with privacy budget of just using 70% or the whole privacy budget, you can again see that there's different of 300 bucks. And when you run on the split data set, so over here, your data is actually different. So first your privacy budget is applied on some data, and then you apply the whole operation on other data, and you actually see the difference of, okay, yet again another difference. But the thing is, it actually works, because if you have a streamlined data, if you're coming a stream data, it's the best way you could actually use this in a better manner. Yep, that's it. Yep. Thank you.
Thanks, Chinmay. Really good to see it in action. And for those of you who are wondering, that's a fairly simple generated synthetic data set that was just used for illustrative purposes. We've got some more complex examples. So if you go to github.com/openmined/PyDP, you can follow the documentation there. We'll actually now move on to another demonstration by Lukasz. So Lukasz has been leading our Java virtual machine team, and he's translated PyDP into many different languages. But this is the one that we'll get him to talk about now as one of his favorite languages, and I'll pass it along to you now. Please go ahead.
Thank you. Let me share my screen. Can you see my notebook?
Very clearly.
That's great. All right, so I also have a notebook demo. This one is not in PyDP and it's not in Python. Instead, it's in Clojure on the Java virtual machine. Our differential privacy team is working with many different languages. So this demo will be in Clojure. The notebook is heavily based on an example from the differential privacy library by Google. So the authors of the original example are Sasha Kulankina, Miraj Vustlat-Basaran, and Yuri Sushko. We really like this demo. It's I think it's very nicely written, very clear. So we are remixing this example and porting it to various languages. And actually, there will be also a PyDP version of it, or rather, we already have a PyDP version of this demo, but it's not available in a notebook format. So this time I'll show you something in Clojure. Don't worry if you can't understand most of the code here. Clojure is a little weird language. It's more important to focus on the story, and also there will be bar charts to watch. So let's skip this part. It's very technical. It's mostly about dependencies and imports. So this story is about Alice. She's a restaurant owner, and she has a lot of data about her restaurant. She decides to publish some statistics, And in order to protect her customers' privacy, she wants to use differential privacy algorithms. So first, let's set the default epsilon. That will be the budget we spent on per query. The first, so first, let's read the data set. This is the data set of all the visits from one day. So each row is a visit. A visit has a visitor ID, time, entry time, minutes spent by the visitor, and money spent during that visit. So Alice has all this data and she wants to produce some statistics. First, for her own use, she might produce a bar chart like this. So this is visits per hour type of statistic, and it's pretty easy to produce. All she needs to do is group those visits by hour and simply count rows. That's what it basically boils down to, right? So grouping by hour and counting rows. And here, for simplicity, in this demo, we assume that a visitor can enter the restaurant only once a day, at most once a day. So now we know, and this will matter in a moment, we know that a visitor always falls into one of these time slots. We have these 12 partitions, 12 different hours, and each visit belongs to one of these, right? So if Alice wants to publish something like this, a similar statistic, but in a differential private way, she wants to produce differentially private values for all these numbers of visits. She needs to call one of the functions from the differential privacy library, which not only counts rows, but also applies the right amount of noise. So she's calling the count function, which accepts two parameters. One is epsilon, that's the budget we spent on a query. And another one is max partitions contributed. This parameter says how many times or how many different partitions at most one individual can contribute to. So we already said, okay, this is maybe not very clear. In general, the more an individual can contribute to algorithms results, the more noise we have to add, right? I hope it makes sense. So in this case, we already said that a visitor can only contribute to only one of those bars, because each visitor falls into one of these time slots. So we set this parameter to 1, and this will result in adding just a little bit of noise, okay? This parameter is also called L0 sensitivity. Well, this is exactly what it's called in PyDP, L0 sensitivity. So this whole function call in PyDP would look like this. We would instantiate count algorithm. We would pass the privacy budget for the query. We would set L0 sensitivity to 1, it's the same parameter, and then call the quick result method, passing all the visits for counting, right? So if we actually compute, if you run this, we can see a bar chart where non-private values and private values are next to each other. So red bars are non-private values, not safe for publishing. The blue bars represent those differential private values, and they're noisy. Noise is added randomly. So if I rerun this, I can see the blue bars are actually changing. And yeah, so you can see that some of the blue bars are higher than the red bars. Some of them are smaller. There's a little bit of noise here, but overall the pattern is preserved. So for instance, you can clearly see which of the hours are more busy, even looking just at those blue bars, right? So this is what Alice would actually publish, only those blue bars. These are the differential private values. And you can learn something from it, but customers' privacy is preserved, it's protected. The private data is protected. All right, so that's cool. In the next example, Alice wants to do something very similar. She wants to produce statistics of visits per day. So first she needs to read a slightly different data set. Here, again, every row is a visit. Each visit has a visitor ID, time of entry, minutes spent, money spent. This is the same thing as before. But now we have this extra value that's weekday. And here weekday 1 means this visit was on Monday. So 1 means Monday, 2 means Tuesday, 7 means Sunday, right? So she would like to, so now now partitions are, again, time slots, but it's not, these are not hourly slots. Instead, one slot corresponds to 1 day. So she again produces statistic, she produces a bar chart similar to the previous one. Now it's showing visits per weekday, but we made some slightly different assumptions here. We are still assuming a visitor can enter the restaurant at most once a day, but we do not limit how many different partitions a visitor could contribute to. So in this example, we allow a visitor to come back every single day, which means every visitor can contribute to 7 different partitions. So we set this parameter to 7 and pass it to the counting function here. So this means we actually add a lot of noise. If we allow every single individual to contribute a lot to the algorithm's results, we need to add more noise. So in some situations, we may be not comfortable with how much noise we're actually adding. And this assumption that a restaurant visitor might come back every single day, maybe it's not that realistic. Maybe maybe in Alice's estimation, the vast majority of visitors actually visit her restaurant at most 3 or 4 times a week, right? So she could make this assumption that maybe her visitors visit the restaurant at most 3 times a week. So she would like to use this parameter now instead of 7. This would result in adding less noise. And she can pass this parameter here eventually. But before she does it, she actually needs to make sure that it's fine to use this low parameter. So it is, in general, it is the responsibility of the function caller. In this case, it is the responsibility of Alice to make sure that the parameters she's using fit the data set. Otherwise, so suppose she's setting parameter 3 here, but actually some of the visitors have more visits per week than 3. Maybe they're coming back, maybe they visit the restaurant 4 or 5 or even 7 times a week. So they contribute a lot to the algorithm's results, but because of the low value of this parameter, we will be adding not enough noise, right? So this would compromise differential privacy. So if Alice still wants to set this parameter to a lower value, she needs to pre-process the data set. So she needs to make sure in her data set there are no visitors with more than 3 visits per week. And this code may be a little difficult to understand, but roughly we're finding all visit days. For each visitor, we are finding visit days, and then we are filtering all visits, discarding. Okay, so I'm sorry. For each visitor, we are finding all visit days, and if someone has more than 3 visit days, we are randomly choosing only 3, and then only 3 visit days, and then getting rid of all the visits associated with the remaining visit days. I mean, I know it's a little confusing, so we don't have much time to spend on this piece of code, but in short, we are pre-processing the data set, getting rid of, like making sure, or we need to guarantee that in our data set, no visitor has more than 3 visits per week. So we get rid of some of the visits, and then we can actually count. We can actually pass this lower parameter to the like we may set L0 sensitivity to a lower value, and these computations. Okay, this bar chart may also be a little confusing. The results will be like this. First of all, the red bars show you the non-private count on the unprocessed data set. The green bars actually show you the true values or unprocessed, so the true values and non-private count from the processed data set. So we have removed some of the visits, so you can see there's a difference between the red bars and the green bars. They're all lower, and blue bars are also lower than the red bars. So this is because we removed some of the visits from the data set. We now have lower values. These are the true values, the green bars, but because we are setting the parameter to a lower value, the L0 sensitivity is now lower, we actually generate less random noise. So this is, sorry if this is a little confusing. we are adding a lot. We are adding less random noise, but we actually have distortion because we pre-process the data set so that all the values are actually now smaller. So this might make sense in some situations because now we are introducing less. It's less random, so maybe some patterns will be more clearly visible, but there will be this this effect that overall the numbers will be lower. All right, so in the last statistics Alice might like to produce is some financial data. So some financial statistics. She would like to produce a chart of daily revenues, and for this, this time she sets L0 sensitivity to 4. We are pre-processing the data set, and this time, instead of simply counting rows or grouping rows by days or by hours and counting them, we actually need to add some values. So because every visit stores the number of or the amount of money spent during that visit, we can produce a dictionary. So for Monday we have a vector of spendings, right? And similarly for Thursday we have a vector of spendings, and we need to add all these numbers. So this is a slightly different situation than previously. We need a different function. It's called bounded sum, and this function accepts more parameters. First is the privacy budget, same as before. L0 sensitivity, how many partitions an individual can contribute to. And now we have 2 extra parameters. So here Alice is estimating that she's estimating that no one pays below €0 during the visit. That makes sense. And also the maximum number of spending, so to say, allowed is 50. Actually, these values will be used for clamping. So we are adding values here. If something is smaller than 0, maybe there are some mistakes in the data, some errors, right? Some junk in the data set. If there's a spending below 0, it will be counted as 0. If someone spends more than €50 during a visit, it will be counted as 50. So we are clamping and adding these values. All these parameters are needed here. And actually, in PyDP, you can use bounded sum without setting these bounds here explicitly. In PyDP, a little piece of the privacy budget will be used to privately infer the bounds. All right, so if I compute this, here's the bar chart, very similar to previous charts. Again, we can see the overall pattern. You can see people spend more on weekends, but there's a little bit of noise so that you can't really see what are the values exactly. And this is the chart Alice might want to publish, only the differential private values. And as the very last thing, I want to say a few words about why is it actually important to add noise to those aggregate numbers? Because it may seem that if you only learn that the total revenue on Monday was 8,600 something euro, it's just a bare number. So what could possibly go wrong if you publish this number, right? How could you retrieve any individual's sensitive data from just a bare number? But actually things could go wrong. And if Alice was publishing these values without any noise, suppose you can learn what the total revenue was on Monday, and maybe somehow you could also learn what was the revenue until 10 to 9 p.m. Like it's possible if Alice was comfortable to publish any aggregate number, maybe you could convince her to publish both numbers, the total Monday revenue and Monday revenue until 10 to 9. So these are both big numbers, aggregate values, and they both seem to somehow hide individuals' sensitive data, right? But if you happen to know that maybe Bob was the last visitor at the restaurant on Monday late evening, and he may be the only visitor to contribute to the difference between those 2 big values, then you can actually subtract these values and learn exactly how much Bob spent during his visit, right? So this is why you actually need to add noise even to aggregate values. And that's why you need PyDP. So you can pip install it today. So thanks for listening. That's it.
Thank you so much, Lukasz. That was fantastic. And it's a tribute to the idea that differential privacy, we want to lower the barrier of privacy preserving machine learning and techniques. And differential privacy is one of those core primitives, one of those core techniques that really does enable that. And it's not just Python users that use, it's not just Python that we need to, who has individual data we need to protect. So we want to bring it to everybody, all different platforms. There are some working demos. If you go to openmind.com, github.com/openmind/PyDP, or you'll see some links there. And there are actually some demos we've got up and running, making it work in Swift. So we've got, and various other mobile platforms. So go check that out as well, and a bunch of other different languages. So big thank you to all of the speakers today. It was absolutely fantastic to see all the work that's been done. A great celebration of the 6 months of effort that it's taken to get here. A special shout out to the Google team. We have been, wrapping their library and then extending it a little bit. And the Google team has done a fantastic job at, helping us out on a few key occasions, including getting us over the Windows hurdle, which was a bit of a tricky one. So right now, we might just do a few before we end today. We've got a few questions, Q&A, on the old Q&A, so I might just move to that. And so I think some of these questions are a little bit academic, so I'll get actual Kritika to answer. We'll start with Kritika anyway as a starting point to answer that. So the first question, are you there, Kritika? Hopefully Kritika.
Yeah, I'm here.
Fantastic. So the first one is, this one's from Gunjan Narulkar. How do you actually compare performance of differential privacy algorithms?
It depends on what you mean by performance. Maybe it could be the way it's getting computed, how long it's taking to compute, the complexity that way, or it could mean how much utility you're getting out of it, probably in the form of a model accuracy or how correct the result is. So based on whatever you're asking for, there's a different answer, but let's assume that we're talking about accuracy. Then in that case, the direct trade-off is that the stronger the privacy that you're going to have, the lower the accuracy. So, you go for very small values of epsilon and delta if you want strong privacy. And in that case, your accuracy is going to go down. And that would be for a specific algorithm. And if you were to look at multiple algorithms, then some will be more efficient in certain cases, and some others would not be. And that would depend on the application and the algorithm that you're using.
Right, thanks, Kritika. So I think the next question, how do you standardize the expectation out of the individual's frameworks and algorithms? I think that's a similar answer. Is there anything you wanted to add there, or do you think it's essentially covered in that first answer?
Right. So one base expectation of differential privacy, whether it holds, that is mathematically proven. So that has nothing to do with implementation. And other expectations, the two main areas would be testing and validation. And so any framework or algorithm that you build strong test cases and validation mechanisms, and that would be the way you standardize expectations.
Fantastic. So Gunjan's actually asked quite a few questions. They're actually not bad. So we've only got 5 questions. So we'll just go through a few more. So from a user's perspective, are there any confidence interval that can be provided so that we can say that the noise has changed the real result, but still the actual result is within this interval? Else you are compromising the quality results and hence usability. Differential privacy, I guess that's about making sure we can be confident that the results we're providing, that we're not losing utility, which is what you tend to do. It tends to be a trade-off with privacy. Did you have something to add specific to that, Kritika?
Yeah, so the only thing that I'll say is that yes, there are confidence intervals that are provided, and they depend on some factors in differential privacy. The main ones being how sensitive your data is or how sensitive your function is, the value of epsilon or privacy budget that you've chosen, and the noise mechanism you've chosen. So as a function of these things, you can calculate what is the maximum deviation that your data is going to face by all the noise.
Fantastic. JMP Triple I asked, the examples today are primarily reflected transactional data sets. Does PyDP also account for fact table data sets, e.g. CRM databases? So, I think what's great is that we have some specific examples up on the repo to look at. And one of the ones that we're working on at the moment is actually with a star schema, or a Kimball style star schema. So the short answer is yes, absolutely, it does support it. It's more about how you implement. So we will definitely provide some examples there. And so you can definitely hit up Chinmay about that, or just go to the repo for some further examples. And on a note as well, is one of the directions that Chinmay is pushing the team is to help extend what we're doing to other systems. And obviously we've got the ETL systems we're extending to, but certainly some specific, fairly famous customer CRM systems are on the horizon as well. So there may even be a very specific answer in the near future to the question you're asking. So thank you everybody for coming today. I think that's about it. Just quickly before I pass back to our fantastic host, I really wanted to just give a shout out to everybody who attended today. Thank you so much for taking interest in this library. It is something that's, it's been a lot of effort to get it there, and we know it's something the community is crying out for. So, and please make sure that as you begin to use it, if you've got any feedback, make sure you put it in that GitHub repo, and don't be afraid to get involved. Go to placements.openmind.org to apply to join our team as well. Special thanks to Helena. So Helena Barmer put in a lot of effort to organize this event. It takes a lot to make these things happen. So I really wanted to just make sure that, we recognize her efforts. And again, Kritika, Chinmay, Andrew Trask, and Lukasz, thank you again so much for putting together your content. And apart from that, I think that's about it. I'll hand across to Helena. Thank you, everybody.
Thank you so much, Ben, and to the whole team. Great talks today. Can we have some thumbs up, the B? So just type a B in the chat just to recognize all the efforts the team have done and to celebrate them for where they at today. This was really great, everyone, and just loved joining in for a little part hosting it. And now I posted how to contact the team. Just join us on Slack. If you can't find your way, just ask in the general channel, and we will be there to help you if you can't find your way around. And I'm just going to post because in about 1.5, I'm a little bit lost in time zones, but I'm posting about the OpenMined research presentation day today as well. So get a free ticket for that as well if you want to just stay and have fun with the OpenMinders. And I also want to say that please get a free ticket for the OpenMined Privacy Conference. I'm posting it here, and you can read more about the conference and the agenda. Speaker is going to be really great. Thank you, everyone. This was really, really awesome. I hope to see you soon again. So thank you, everyone who joined us, and hope to see you at the OpenMined research presentation or at the privacy conference. And even better, in Slack, so we can chat as well. Bye, everyone. Have a really lovely Saturday. Thank you.